Understanding the building blocks of voice gateways, gatekeepers, IP to IP gateways, and voice protocols. You see a stack of books there because I'm getting the books out on you. The Gateway Gatekeeper series is typically, I'm not saying always, and I'm not saying you're in the wrong place if this isn't the last one, but it's typically the last CCVP certification series that people jump into because it takes a lot of the pieces from everything and compiles it all together. So what I want to do is I want to pull the books out on you. I want to go through the building blocks of voice over IP networks. Now some of these you may have seen before in other CCVP courses or maybe brand new to you, like voice gateways, like gatekeepers, like IP to IP gateways, defining what all these different pieces are and where they fit in the network and then how they tie together using voice protocols. Well, let's start off with the device we'll be spending most our time on in this series, and that's the voice gateway. When you first get into the realm of networking, one of the questions you'll have to answer is what's the difference between a router and a gateway? And most of the time, if you're going through the routing and switching path, people use it interchangeably. They go, oh yeah, your default gateway. What's your default gateway? Oh, it's a router. Well, what's the difference between a gateway and a router? Well, there's not really too much difference. They're kind of the same thing, and most of the time in the data network they kind of are, to where a router and a gateway are used interchangeably, that term is. But a voice gateway literally means, and gateway in general means, moving from one network type to another. So, for example, the reason we don't use gateway as much as router anymore is because the data network, all the protocols have faded away. We used to translate from TCP/IP to IPX/SPX to AppleTalk to DECnet to all these different protocols that existed in the networking landscape. But now, since everything's TCP/IP, it's kind of like, oh, well, we're routing through a gateway. It's just kind of an interchangeable thing. Well, voice gateways move data from one network type to another, meaning we're moving typically from a voice over IP network down here into a network like the PSTN, to where this voice gateway gives us an interface to the PSTN. It might give us an interface to TDM equipment, the time division multiplexing equipment, like a PBX system or a key system. So maybe we have a network that's kind of a hybrid. We've got, a small little voice over IP segment over here, and then we have a gateway that's linking it to the PBX system, and we're communicating between these two different styles. We can use voice gateways to relay DTMF tones, and now we're getting to some of the requirements. The voice gateways have to relay DTMF tones. That's dual tone multi-frequencies. You're looking at your telephone keypad, you got 1, 2, 3, 4, 5, 6, 7, 8, 9. Obviously a garage sale keypad here. When you push those, you hear the beep, that's a DTMF tone. The gateways have to be able to relay those through. And there's many ways they can do that. They can play the sound, they can convert it to a text file and just send the digit as ASCII text, but it has to relay in some way those tones that are being dialed. You also have to support call services like hold and transfer. And it sounds kind of like, okay, well, why are those such a big deal? What's the story? Well, when you have an IP phone or a phone over here connected to your voice over IP network, and you're talking, you go, oh, hold on one second, and you push the hold button, technically behind the scenes, that phone drops the call. It hangs up on the call. It's no longer responsible. So that call has to fail over to some other device that's holding it while it's on hold. Technically, we call that a media termination point. And that can be either the voice gateway, could be a call manager server over here doing that. But services like hold and transfer do that sort of function. You also use voice gateways to communicate with IP telephony devices like the Cisco Call Manager. So we have PSTN calls coming in, people dialing our corporate number. The voice gateway translates those calls and sends them over to the call manager, who then figures out where to direct them. Now we also have to be able to support analog or digital interfaces, and you might even add an "and" in here as well, because a voice gateway can support both. Analog being your connections to a PSTN or an analog phone, for instance, on an FXS port. Those interfaces allow one call per port. Analog, one call per port. Digital, that's where we get into our T1/E1 connections. Those are where you get multiple calls per port, and those tie into typically PSTN and PBX devices. So that's half the series title, right? Cisco Voice Gateways and gatekeepers. So what's the scoop behind the gatekeepers? Well, I'll start off this discussion by saying that gatekeepers are typically in larger organizations. Not always, but typically. Because gatekeepers are focused around centralization, providing a centralized point of all this stuff: address resolution, call admission control, security, and so on and so forth. And that's typically needed in the larger organization. For example, if you've gone through Cisco IP telephony, or CIPT, which is all about Cisco Call Manager, you know that Call Manager is designed in a cluster formation. And if you haven't taken the CIPT series, then let me give you a flyby overview. A cluster is a group of call managers that are focused on supporting IP phones. You will have a publisher, which is a read-write copy of the database, and up to 8 subscribers inside of that cluster. Now, you can design that cluster to where all these call managers will support IP phones. And you can even have clusters go across geographical boundaries. But normally, a cluster is within one geographical region. For example, this is Arizona. Maybe over here is California. Now, I could, if I had the ability to, put some subscribers over here in California that belong to the same cluster as Arizona, but the requirements for that are I'm thinking obscene, but that's not the right word. It's astronomical. That is a better word. The requirements is that you have less than a 40 millisecond one-way delay between these locations. Now, I chose Arizona and California because they're pretty close physically, a few hundred miles apart. So it's feasible that you could do a split cluster in these. But if you had Arizona and, for instance, Florida, New York, or let's throw Japan over here, it's impossible. You can't physically make it from Arizona to Japan in less than 40 milliseconds, one-way delay. So in general, most people will just say, well, every physical location is its own cluster. Now, this is, typically how people design it. California will have its own publisher and subscribers, and Japan will have its publisher and subscriber, and they'll divide it up to where extensions exist in each one. Like maybe Arizona is every extension that begins with 1 XXX. And California is 2 XXX, and Japan is 3 XXX. So if I have a phone in Arizona, let's say 1001 is this extension, and he dials 1002 down here, no worries. The Call Manager cluster, it's in the SQL or Oracle database, depending on what version of Call Manager you're using. And it will look it up and say, oh yeah, 1001 to 1002, no problem. Ring! The phone rings, database lookup succeeds, and life is good. But let's say 1001 dials 2001. Well, at that point, Call Manager is going to go, I don't know how to get there. It's not in my own cluster. So what I have to do as an administrator is create a route plan. And for those of you that have been in CIPT, that's where you go through the route pattern to the route list to the route group. I mean, if you've been in CIPT, you've probably seen that so often you can sing it. Route pattern to the list. I mean, it's just you see it again and again. How to create these route plans between each one of these locations. So California to Japan, Japan to California, Japan to Arizona. Create this route plan to go here, and Arizona to Japan. You start creating these links that link your cluster. Now, with 3 clusters, it's feasible. I can do it. It's just 6 different links that I'm creating. But once I bring up the 4th cluster over here, and the 5th cluster, and the 6th cluster, I mean, by the time you're up to 10 clusters, you're looking at potentially 100 links going between them. It's exponential. It just keeps on growing. I actually talked to somebody about who's running a call manager deployment for a school district, and he said, yeah, it's great, but the management is just, it's insane. I said, well, what do you mean it's insane? He goes, well, we've got 13 sites, and we're, to configure the route plan between these guys is just crazy. And I thought, I was like, 13 sites where you're doing this, that is crazy. I mean, think of it as like 13 routers with a full mesh relationship. I mean, if you want to take it to data world, I mean, every router has to have a connection to every other router. I mean, it's just, just crazy. You can't do it. It just becomes unmanageable. So I say all this to say this is where the gatekeeper comes into play. Rather than these clusters, and I'll write their names up again, Arizona, California, Japan, linking to each other, they all have a centralized point, and this is what I'm talking about, of address resolution. So where Arizona still knows it's 1XXX, but when somebody dials 2XXX, Arizona doesn't know that that goes to California. It will send the message up to the gatekeeper and say, help me out here, bud. How do I get there? And now the gatekeeper becomes your centralized point of administration. You do all your configuration right there. So the gatekeeper knows, oh, well, to get to 2XXX, you go here. So what it does is it tells Arizona in response, California is over here at 10.1.1.2 is maybe the call manager's IP address over here. So Arizona goes, oh, great, thanks, and just goes over and contacts them. It doesn't go through the gatekeeper, because otherwise that would be a lot of overhead for the gatekeeper, but the gatekeeper acts as that centralized point of resolution. It can act as call admission control, like are you allowed to call California? Of bandwidth control, like is the bandwidth available to call California? And there's many others. We'll get into all these when we get into the gatekeeper specifically, but it does centralize everything. Now, I have the gatekeeper floating out there, and you'll see it in a lot of network diagrams. It's kind of like this like where is that router? I don't know. It's floating. It's there. It's out there. It's not normally what you won't have like a site with just a gatekeeper. A gatekeeper will usually be in like your main site will be the gatekeeper, or maybe you'll have a couple of redundant gatekeepers in case one of them goes down. But these become your central point of connectivity, and they are the central point of everything in your network. Now we move into some of the potentially new devices. And I say it that way because if you've gone through any of the previous CCVP series like C-Voice or CIPT, you've probably seen gateways and gatekeepers before, if not in concept, but in configuration as well. IP to IP gateways most people haven't heard about. And what an IP to IP gateway is really the future of voice over IP networks. It acts as kind of a demarc point between voice over IP networks. And when I say that, I think about demarcs, as in if you get let's say this is your home or your business, you get a new data connection brought in, the service provider trenches, up the ground, dig, and then they install a box on the side of your home or business and have a wall jack inside, and they say, that is our point of demarc, or demarcation, meaning that's where the responsibility passes. If something over here breaks, that's our business, and if something over here breaks, that's your business, and you have to fix that. Well, this provides a demarc point, or a line of responsibility between voice over IP networks, because this really is the future. I mean, we could see two different scenarios. We could, in the future, see things like Sprint, who's a major telecom service provider, and you might see over here AT&T. Now, in the future, everything is voice over IP. I mean, everything. Every home, every business, everything is moved to voice over IP. Now, don't hear me wrong. I'm not saying everybody's going to have a IP phone sitting in their home. For example, if I were to look at my house, I have voice over IP phones inside of my home, Cisco IP phones, because I'm weird. I like that kind of thing, and those are what run my phone network in my home. So I'm speaking voice over IP natively out of my house. But if I look at my neighbor, her name's Julie. I've got Julie's phone over here. She doesn't have a voice over IP. She has a normal analog phone, and she'll probably have a normal analog phone for years to come. And that line goes out of Julie's house and links up to a service provider over here. And that service provider, that might be the Sprint or the AT&T out here. The service provider has some kind of device either attached to the side of her house or at the service provider's central office over here. Who knows where it'll be. But that device will convert her audio, the words that are coming out of her mouth into the phone, into voice over IP before it enters the carrier network. So in essence, even though we're not using voice over IP devices everywhere, everything will become voice over IP. And that's where you're going to see, the internet becoming the primary backbone, or the internet 2 by that point, running all IPv6 everywhere. And you're going to see all these different service providers, and they need a dividing line between them. Not only for privacy, Sprint can't just jump into AT&T's network and do things over there, but also as lines of responsibilities, like Sprint's network is Sprint's network. It doesn't blend in with AT&T. And I used a firewall icon to kind of represent this IP to IP gateway. It's really just a router, but I thought the firewall icon would paint a good picture of it. That this is the demarc point. This is the line of responsibility. Now this could very well be, instead of service routers, this could be you. This is your cloud. This is your business that is running voice over IP. And over here, AT&T could become, for instance, one of the ITSPs. ITSP is an Internet Telephony Service Provider, meaning that when people dial out of your network, right? They're sitting in here with a phone. They dial 9 to get an outside line, and they hear the second dial tone, and they're starting to dial an outside number. A lot of companies are beginning to use Internet Telephony Service Providers, which is an organization that they can send the call via voice over IP to that organization, and that organization, the ITSP, sends it out to the PSTN. And using an ITSP is much more efficient, much more cost-effective than the traditional telephony service providers, where you get, for instance, a T1 line or something of that nature to the PSTN. But that's where we would need that IP to IP gateway, because our network, your network, is not AT&T's network. We have to have this line of responsibility. Now, this IP to IP gateway not only provides a demarc point, it also can translate protocols. Like, for instance, maybe you're using H323 inside of your network, and the ITSP uses SIP. Well, the IP to IP gateway can translate that. It can also translate codecs, like maybe you're using compressed audio inside of your network, and it needs to become uncompressed as it goes to the ITSP. IP to IP gateway can transcode between codecs. It can provide call admission control, like am I allowed to make this outgoing call? It can provide a level of security. The reason why is this also can act as a NAT firewall for your phones. For instance, maybe you're using, and most likely will be using, private IP addressing inside of your organization. Well, you don't want those private addresses. Matter of fact, they can't. They can't go across the internet to an ITSP staying a private address, so the NAT firewall can convert them to a public. Now that's great because now you can cross the internet, but it also allows you to hide your private addressing scheme behind a firewall type device to where your internal addresses are not being exposed to AT&T or anybody else on the internet for that matter. And then it also provides billing capabilities where it can track certain minutes, how long you were on that call, and provide billing support to different groups inside of your organization, or dividing Sprint and AT&T, where Sprint has to send AT&T for certain numbers of tie lines being used or minutes being used on their network. So the IP to IP gateway really is that firewall, that demarc line between these voice networks. There's one more thing I want to talk about in this nugget. And I saved the best for last. This is one of those scary slides where you see it and you're like, that's a lot of stuff. But don't worry. This is just a preview of what's to come throughout the rest of the series, and that is the voice protocols. Each one of these protocols has a specific section dedicated to it. You can look at the table of contents of this series and see there's a specific section dedicated to each one of these protocols in the series. I just wanted to give an overview of where these all fit, and as before, if you've gone through some of the CCVP track previously up till now, you've probably seen some of these protocols before. For example, I'll start off with the most common, and that is H323. H323 is the most common because it's archaic. It has been around since, well, for a long time, since the 80s. It was originally designed to give you multimedia experiences over data lines, specifically focused on ISDN. When ISDN came out with their BRI and PRI flavors, people were like, oh, this is the future. This is the future of everything telecom, and we're going to have video. People were talking about video calls and all that kind of stuff even back then. And so H323 was developed as the protocol to communicate over that. So the benefit of that, I'll give you the plus, is it's got history. It's been tried, it's been true, it's been tested, it's solid. It's a solid protocol. The drawback is it's huge. It's a massive protocol suite, which is designed for voice, video, and data, meaning it's able to do everything in itself. It's not relying on other protocols. The H23 is, just like TCP/IP, a protocol suite where it's got protocols that can do data sharing. It can do video conferencing and video streaming and that kind of thing. It can do voice over IP, all within that protocol suite. Now, I emphasize that being a large protocol suite or suite of protocols because its successor which is SIP, I'm going to talk about that in a moment, is very similar to H323, but very streamlined. And I'll, again, talk about that in a second. So H323 is a distributed peer-to-peer signaling protocol. And what that means when I say peer-to-peer is that it's designed in such a way that if we've got a router here, let's say that we've got this router that is taking this phone right here and connecting it to this router and this phone over here. H323 is designed in itself, these are squished phones, to be peer-to-peer, meaning when this phone dials, we'll say 1111, which is this phone over here, it hits this router, and this router is supposed to have a dial plan in itself that says, I know how to get to 1111. And it says, oh, that points over here to this router. And this router has a dial plan saying, well, I know how to get to 1111. And it makes this phone ring. And if this phone dials 2222, which is maybe this phone on the other side, the same thing happens. They all have to have dedicated dial plans in themselves. They're peer-to-peer devices that tell them how to get to other places. Now we can simplify and consolidate that using devices like a gatekeeper. A gatekeeper, like I just mentioned a couple of slides ago, is an H323 device where you can now centralize that dial plan on a gatekeeper right here. But it's not part of the default configuration of these devices. So you'll hear things like terminals, like gateways, like gatekeepers, like MCU, multi-point control unit devices. Now, that is H323. Again, that is my high-level overview I wanted to give you of the protocol. But I want to make sure I emphasize that H323. Let me flip colors here. H323. Put little checks. SIP. MGCP, and Skinny down here. Every single one of these are voice protocols, but they are focused on signaling. They are signaling protocol, meaning they do not carry audio themselves. H323, SIP, MGCP, Skinny, it doesn't actually carry audio. As you're speaking words, they're not being sent using H323. H323 is signaling. SIP is signaling. It is responsible for setting up the call. It is responsible for handling features during the calls and all that kind of stuff. There's only one streaming protocol that actually handles the audio, and that is this guy right here. RTP, the Real-Time Transport Protocol. More on that later. I just want to emphasize signaling. That's what these are. Now, SIP is designed as the replacement, the next generation H323. It is, just like H323, a distributed peer-to-peer signaling protocol in the same fashion. It is designed, though, with clear text signaling, not encoded like H323, based on internet standards. What that means is let's say I'm doing a debug, right? If I'm doing a debug with H323, when somebody places a call, it's going to be blah. It just dumps stuff on my router screen, my terminal, and it says we've got a code 0x59692B3, and I have to look at my reference book and go, what is an X59692B3 code mean? And I've got the explanation spelled out for me. That's an encoded H323 method that means ringing or something like that. It tells me ringing. Now, the SIP is so much better because it's all done in clear text. Meaning, when I make a call, it says ringing right in the message. I don't have to look up what's ringing. It's ringing. Or if it's busy, it says busy. It's very clear text. It's very simple to understand, and it's based on internet standards. The same group that developed HTTP and DNS and things like that developed SIP. So it uses very familiar things like phone numbers are seen as email addresses and things like that. So SIP, very, very simple to understand. It uses user agents, proxy, redirect servers, registrar servers, and present servers. And proxy is a type of server as well. These are all different kinds of servers, all of these guys, that run the SIP networks. User agents, these are your phones. These are your routers that are making calls that are going through. All of these different server types are the servers that run it. Now again, high-level view, we'll be breaking all of those servers down in the nuggets dedicated to SIP in this series. MGCP was developed by Cisco as an industry standard. And I want to make sure everybody catches, MGCP is not Cisco proprietary. A lot of people think it is. It is an industry standard, and it is the only centralized client-server signaling protocol. Meaning, all these other guys, peer-to-peer, peer-to-peer. They're all peer-to-peer. This one is centralized, meaning that I could take, for instance, a call manager server and control a bunch of routers using MGCP. At that point, the routers don't require much configuration. They just need to know how to get to their call manager server and to put their interfaces under call manager control. That's MGCP. All of the administration is done from the call manager server, or what the industry standard calls a call agent. Call manager is Cisco specific. So an organization that's huge, has a lot of different routers, a lot of different devices, would definitely prefer MGCP in a lot of cases because the devices themselves don't have to be configured with too much configuration. They can all manage it from a central entity. All gateway intelligence is relayed from the call manager or call agent that is set up. So very, very centralized, very central configuration oriented is MGCP. Let me skip RTP. I'll come back to that in a second. The last signaling protocol is Skinny Client Control Protocol. This one's a quick one. It's easy. This is truly Cisco proprietary. It is used to control Cisco IP phones and some gateways. They're very limited gateways, like a VG 248 would be one of the gateways, and that provides 48 FXS ports. It's really just a bunch of devices that gateway provides into the network, and so they use Skinny to control it. But Skinny is by default the default protocol that call manager uses to control the IP phones, Cisco IP phones. And using Skinny, you get the full feature set. Now you can use other protocols like MGCP, like SIP, to control IP phones, but you're only going to get a limited feature set because, well, I'll get into this much more later. But SIP and MGCP don't have all the tweaks, the industry standard methods to control all the features of a Cisco IP phone. I'll leave it at that. More on that later as well in the SIP and Skinny specific nuggets. The last one I want to mention is RTP. This is the sound of your voice. This is when you're speaking into an IP phone and you're saying, "Hi, how are you doing?" These are the words that are coming out of your mouth. As a matter of fact, you, listening to me right now, are hearing me over some type of RTP stream, a real-time transport protocol. I'm guessing. I don't know all the specific CBT nuggets, ways of streaming audio, but chances are you're hearing me over some variant or some form of real-time transport protocol audio that's being streamed to you, my voice. You're not actually hearing my voice. And this is what creeps me out. Creeps me out to this day to talk about how this works. But what's happening is as I'm speaking, the processor behind the scenes is taking every sound that comes out of my mouth, and I say the word. I say woo. You know, the very first W of the word. It's saying, okay, woo. Let's convert that. That's a 1011010101. It's converting me to binary. You're hearing, not me. You're not hearing me. I'm not Jeremy. You are hearing a digital representation of me. The sound that you're hearing is a reconstructed version of my voice that is good enough to allow you to recognize me by tone. You can tell what my tones are when I speak quietly or when I get really excited. You can tell that because it's able to digitize that and turn that into binary values, but you're not hearing the full scope of my audio. Man, I so just want to digress into Nyquist theorem and all that, but I won't. I'm not going to do that now. RTP is the sound of your audio. Now, RTP rides on top of UDP. It's unreliable, and that's good because we don't want to be able to resend audio if it fails. I mean, the time has passed. It's all real time. So it uses UDP, but RTP, this protocol, adds sequence numbers and timestamps. UDP doesn't have sequence numbers and timestamps. And what that does is when the audio gets to the other side, like right now I'm speaking to you in Phoenix, Arizona, and it's going to some CBT Nugget server somewhere in Oregon, I believe, and then it's being streamed to you from a server in Oregon in some sort of order. I guarantee you the packets are getting there in some kind of random order, and the device before you hear me has to put them all and reassemble them all back in order. Now, of course, I'm relating CBT nuggets to audio and things like that, and there's a lot of comparison, but it's very similar to IP telephony, where as you're speaking into a phone, everything is getting shuffled and put out of order if you're taking multiple paths to get to a destination. Sequence numbers and timestamps let you put them all back in order and see what kind of delay has occurred from the minute I say the word until you hear it. All right, that's enough for one nugget, enough building blocks of voice. So to hit the high points, we have talked about the role of voice gateways, what they do converting between audio types and typically from a voice over IP to a non-voice over IP network of some sort, and can do many features in between as they do that, like relaying DTMF voice, like supporting features like hold and transfer as media termination points, and we'll dive deeper into those concepts. And I think I'm done saying we'll dive deeper into this because this is the overview. That's what the building blocks are. We will explore each of these deeper throughout the series. We also saw the role of gatekeepers. And if there's one word to describe gatekeepers, what would it be? Centralized, right? Centralization of your resources and centralization of your dial plan, your security, everything, to where everybody's looking to the gatekeeper for a centralized pool of blah and all those things that we talked about in the gatekeeper. We also saw the IP to IP gateway, which is kind of like a type of firewall, if you will, for your voice over IP network, separating your voice over IP network from others. And then finally, we looked at the voice protocols, the signaling protocols like SIP, MGCP, H323, and Skinny, and then the sound of your audio, which is RTP, all of that allowing voice over IP communication. I hope this has been informative for you, and I'd like to thank you for viewing.